All right, welcome back, everyone. Still looking at how to derive units of derived quantities in physics. I appreciate every one of you have been following up my video lessons and have subscribed to this channel. Thank you very much. And as we continue, we want to look at how to arrive at the units of some more derived quantities. So in the last video, we went through a number of derivations of physical quantities. You can see that derived quantities, pressure, how it is derived, SI unit, and so on and so forth. Then we saw that of momentum, specific capacity, the SI unit, joules per kilogram per Kelvin, and then also went on to derive the SI base units of a specific capacity. How about electric charge? You can see that there. Potential difference, you can see that in volt. I can also see the SI base unit of potential difference. How about resistance? Because this particular what we have derived here is very important, especially for those of you that are going to take Cambridge exams, Cambridge advanced level exams. They require you to know this. Most times, to ask you to state the SI base units of potential difference. You must know how to arrive at something like this and even this. So this video is not just made for those writing Nigerian exam, Nigerian syllabus and all that, or learning Nigerian syllabus. It's also very okay for those of you preparing for international exams like Cambridge examination. Okay, so I continue from there to look at number 15. Okay, that one was number 14. Number 15 here, I have capacitance. Capacitance of a capacitor. How do we define the capacitance? C of a capacitor. It is the ratio of the charge to the potential difference between the terminals of the capacitor. And the charge, of course, the SI unit of capacitor, the SI unit of capacitance is the farad. Come over here, we have the farad in honor of Michael Faraday. Farad F is the SI unit of capacitance. We want to look at the derived units and probably the SI base units of capacitance. So derived unit is charge is coulomb, potential difference is volt, so it is coulomb per volt, meaning that 1 farad is equivalent to 1 coulomb per volt. Okay, but how about in SI base units? Can we give the units of capacitance in terms of the base units? Charge is given as ampere second. That is, electric charge is the product of current and time. That is ampere second divided by volt. Now, potential difference. In the last video, when I turn this my paper, I have potential difference. The SI base unit of potential difference, kilogram meter square per ampere, and S raised to power what? -3. So that is what I'm going to use here as the unit. So I have kilogram meter squared A minus 1 S minus 3. So when I divide this by this, I have kilogram. The kilogram goes up becomes -1. That is the power, the superscript. Where meter goes up becomes -2. Now this ampere has a power of 1. This is A1 divided by A raised by -1. When you apply the rule of indices to divide two indices divided by A raised by -1, I'm going to have A raised by 1 minus 1 minus 1. That give me A raised by 1 plus 1, which is 2. So this is ampere raised by 2. And then this is S raised by 1. When I divide that by this, it will give me 1 minus -3. That is raised to power 4. So this gives me the SI base unit of capacitance. Cambridge may ask you to state, to give, to derive, to write down the SI base unit of the capacitance. So that is what it is. Then number 16, I want to look at electric field strength. Sometimes they call it electric field intensity. This one expresses the strength of an electric field. The symbol is E. Here, if it's a uniform field, it's defined as the ratio of the potential difference over distance. That is, uniform field is a field between two parallel plates that is maintained by potential difference V, and the plates are separated by distance D. Potential difference, that's what I have here again, that is kg in SI base units, meter squared, A minus 1, S minus 3, divided by distance, which is in meter. So its SI base unit is kg meter raised to power 1, because this and this, when they simplify, what is left is just meter, or meter raised to power 1, A raised to power minus 1, and S raised to power minus 3. Okay, this is the SI base unit, but its SI unit is volts per meter. Volts per meter, that is volt for potential difference and meter for distance. So I can write it here, volt per meter is the SI unit. What is volt per meter? Do you know that it's equivalent to Newton per coulomb? Yes, how do we show that volt per meter is equivalent to Newton per coulomb? Because uniform electric field, according to Coulomb's law, has been defined as force per unit charge. That's electric field strength for a non-uniform field, force per unit charge. So the force is in Newton and the charge is in coulomb. So that gives you Newton per coulomb. And by the time you break this down, you come to see that Newton per coulomb is equivalent to volts per meter. Okay, now let's see one or two more before I round up this session. We're looking at magnetic flux density. Magnetic flux density. So this quantity is a property of magnetic field. It expresses the strength of a magnetic field at some point, some distance from the given body that is producing the field. Magnetic flux density has to also do with the number of lines of force that is, it's passing through unit surface area. So we can also define magnetic flux density as force over length times current. Okay, this is another way of defining magnetic flux density. Its SI unit is Tesla, in honor of Mr. Tesla. Tesla T is the SI unit. You can also give magnetic flux density in Weber, because here we are saying that it's expressing magnetic flux over area that is now given in Weber per meter squared. If I'm going to use Weber per meter squared, this MWB is spelled Weber. Unit of magnetic flux. This one is unit of magnetic flux. Magnetic flux has to do with the magnetic lines of force. When I say magnetic flux, I'm talking in terms of the lines of force. That most times from a bar magnet, they leave the North Pole and then they move into the magnet through the South Pole. So we call that magnetic flux or magnetic lines of force. It's more of a measurable physical quantity. Okay, so how do we derive the unit of magnetic flux density? From this definition of magnetic field strength or flux density, force over length times the current that is passing through the conductor. This formula is coming from the fact that when a conductor that carries current is placed in a magnetic field, that conductor immediately experiences a force. So that force in Newton is given, of course, is given in Newton as N per meter per ampere. Now, this is one of the derived units of magnetic flux density. But in terms of base units, what are the base units of magnetic flux density? Okay, that is F over current times length. Kilogram meter per second squared is the base unit of force, divided by meter or ampere for current and meter for length. So this meter cancel this meter. That gives me kilogram ampere minus 1 second minus 2 as the SI base unit of magnetic flux. You can see that almost all these derived quantities, they can be expressed in terms of base units, fundamental units. That's what we call them, fundamental units, because all the other quantities derived, they are derived from one, two or more of these base quantities, fundamental quantities. See that now? Okay, let's take the last one, number 18, inductance. There are others, but with this now, you should be able to derive, or even if you don't know beforehand, arrive at the units of a particular derived quantity. Even if the quantity is not stated, you saw the unit. You are given the parameter okay, it is so number and they place the unit. You can just, from the knowledge of how to derive the units of derived quantities, you know that this particular parameter refers to this fundamental or this derived quantity. So inductance, from the formula, the potential difference between the terminals of a coil, because inductance is derived from inductor, is given by the inductance multiplied by the current over time taken. I would have said inductance multiplied by change in current, sorry, over change in time. Change in current over change in time. So the inductance, the symbol is L. If I make that the subject of the equation, I'm going to have I'm going to have L is equal to potential difference times T, that's time, over current I. So the SI unit of inductance is the Henry H, in honor of Mr. Henry. I can have an inductance of, for instance, 5 Henry. You see that now? That's the unit of inductance. But what about the SI base unit? What about the SI base units of inductance? We write it like this. Unit of potential difference, SI base unit is kilogram meter squared A minus 1 S minus 3 over, okay, multiplied by the unit of time, which is second, over the unit of current, which is ampere. So that we can now write down the SI base units of inductance given as kilogram meter squared. Now this is A minus 1 divided by A. That gives you A minus 2 raised to the power minus 2 rather. This is S raised to the power minus 3 multiplied by S raised to the power 1. The rule of indices says if you multiply two indices, you add their powers. This is minus 3 plus 1, that is minus 2. So this gives the SI base unit of inductance, where the SI unit is the Henry. Okay, so we have seen about 18 derived quantities. There are still more, but I'd like you to go do your own personal research to get to know more about these derived quantities and how their units are derived. Okay, so the next video I shall be looking at dimensional analysis, which is quite similar to what we have just done here. But then I'll be able to spot out some slight differences between units and dimensions, that they're not exactly the same. All right, see you in the next video.